right? The temperature required to obtain the single phase austenite. Okay, single phase austenite microstructure before quenching, right? Before quenching has been lowered, like what you can see, right? Has been lowered. So, what is the advantage of operating at a lower temperature? A lot of advantages. Okay, so this will prevent cracking of material. Okay. During quenching. Okay, so that's one advantage. Consume less energy. Okay, that's another thing, and reduce geometric distortion. Okay, so if we were to introduce carbon, okay, this is the best range, okay, 0.7 to 0.83, because to get martensite, you have to quench. You have to, right? So you heat up to single phase austenite, FCC. You can introduce your carbon. Then after that you quench, and this is the best range of carbon that you should operate on. Okay. So the next thing that we're going to talk about is quenching medium. Here we're going to look at quenching medium. So quenching medium, you have water, right? As you can see, this is water. It is effective quenching medium due to its high heat or vaporization. Okay. So what it means it requires a lot of energy to transform it from liquid to vapor. Okay, and where is this energy from? It's from your material that you have heated up. Okay, so the bad thing, okay, about water, it oxidizes. Okay, it will oxidize ferrous material. Okay, that is water. And then the next one, you can use brine. So brine is water plus salt. Okay. So it has, so when you use brine, okay, it has faster or higher cooling rate. Okay, faster or higher cooling rate when compared to water. The downside, the bad, is it both oxidize and corrosive. The corrosive is because of the what? The salt. The next one is oil. Okay, oil. It has slow cooling rate. Now, slow cooling rate does not mean it's no good. Okay, it's good in a sense that you don't want your part to be distorted. Okay, if you cool too fast, your part will be distorted. If you cool slower, your part will not be distorted. Okay, so the bad thing about oil, as you all know, especially now, it's expensive to purchase. Buying is just one thing, okay? And unfortunately, and purchase and disposal. Okay? And unfortunately, toxic fume are generated, unfortunately. Okay? So this is for oil. And the last one has the slowest. Okay? The slowest cooling rate is molten salt. Okay, so this is the slowest cooling rate. Okay, and is bad. Same thing like brine. Okay, it's bad because it will oxidize and corrosive. Okay, same like spell corrosive. Double R. Okay. So these are the quenching medium that we can use. Okay. Right. So another part of heat treatment, another aspect of heat treatment that is as important or critical is one. Okay, it's as important or critical is known as residual stresses. Okay. So what are residual? You seen earlier, right? I wrote unwanted tensile residual stress, and I will tell you why is tensile unwanted. Okay, so what is residual stress? So stresses that are locked, okay, into a material as a result of combined mechanical and thermal loading induced by manufacturing processes. Okay, so there are two types. Of residual stresses. So one type is known as the tensile residual stress. And this is positive, but it's also classified as unwanted. Okay. If you have this, it is bad news. And later on, I will tell you why. And the other one is compressive, residual stress, and it's negative, and it's usually the wanted. For the first time, other than your bank account, all right, you want something negative. Okay, if it's your money, you want it to be positive, yes or no? But this case for residual stress, you want the minus. Okay, the negative is good, the positive is bad. Okay. Right. So let's dive into tensile. Let's dive into tensile residual stress. Okay. So why tensile is known as the unwanted? I'm going to write a statement first. Then once I show you, say, oh, that's why it's bad. That's why it's bad. Okay. So micro cracks. Yeah, micro cracks are usually generated in most manufacturing manufacturing processes. Example, metal cutting, forming. Okay. So in tensile residual stress, remember there are micro cracks. Okay. The word to look for is micro crack. So over here, this is known as our micro crack. Okay. So remember at this stage, okay, the applied stress is 0. Okay. So there's no applied stress at all. Okay. And there's a micro crack, okay, or micro crack tip. So when it's tensile, as the name implies, okay, is pulling the crack open. The longer the arrow means the higher tensile residual stress. The shorter the arrow means the lower the value. So you can see that this is bad news, yes or no, right? You have no stress, but you have a micro crack and you have all this orange bit that I've drawn are your tensile residual stresses. Later on, probably after the break, I'll tell you how this is formed, okay, the mechanics of it. But for now, we know that tensile residual stress is no good. And if you were to ask me, what is the size of the crack? So if I'm going to draw a scale, approximately about this length is 10 micron meter. Okay, so that size, okay, the relative, okay, that size over here is 10 micron meter. Can you all figure out how much is 10 micron meter? Anyone? Can you all visualize what is 10 micron meter?
Divided by 25.4.
What do you mean divide by 25 or 24? Micron meter. How big is